Electric current and circuit. Electric current is expressed by the amount of charge flowing through a particular area in unit time. In other words, it is the rate of the flow of electric charges. In the circuit using metallic wires, electrons constitute the flow of charges. Conventionally, in an electric circuit, the direction of electric current is taken as opposite to the direction of flow of electrons, which are negative charges. If a net charge Q flows across any cross-section of a conductor in time t, then the current I through the cross-section is I is equal to Q divided by T. SI unit of electric charge is equal to Coulomb, is equal to 6 into 10 raised to the power 18 electrons. Electric current is also shown as ampere or A. 1 A is equal to 1 C divided by 1 second, or flow of 1 coulomb charge per second. The instrument measuring the electric current is called an ammeter. It is always connected in series in a circuit. Electric potential and potential difference. What is electrical potential? Let us explain here. Look at the electric field. We move a unit positive charge from infinite to points. So we need to work for that. Yes. Thus, electric potential is defined as the work to be done to move a unit positive charge from infinite to the definite point. What is potential difference? The unit positive charge have to move from point P to Q, so the work needed to be done is the potential difference between these 2 points. It is defined as the amount of work required to move the unit positive charge from one point to another point. Mathematically, potential difference V between the 2 points is equal to work done W divided by charge Q, W divided by Q. The SI unit of electric potential difference is volt or V. Now we know the physical analysis. Look at this step. There is a pressure difference in these 2 points. Now open the tap. We notice that the water flows from high pressure region to low pressure region till the pressure becomes equal. Similarly, in electrical field, the electrons flow from high to low potential region. If the potential differences are same, so no current will flow through the conductor. Ohm's law. George Simon Ohm stated that the electric current flowing through a metallic wire is directly proportional to the potential difference V across its ends, provided its temperature remains the same. V is directly proportional to I, or V divided by I is equal to constant, is equal to R, or V is equal to IR. R is the constant for the given metallic wire at a given temperature and is called its resistance. It is the property of a conductor to resist the flow of charges. Look at the data. If we plot a graph between the potential difference versus current, we observe that as the current through a wire increases, the potential difference across the wire increases linearly. This graph obeys the Ohm's law. Resistance. Resistance is the property of a conductor to resist the flow of charges. Let us study electrical resistance of a conductor with the help of an activity. Take a nichrome wire, a torch bulb, a 10-watt bulb and an ammeter 0 to 5 amperes range, a plug key and some connecting wires. Set up the circuit by connecting 4 dry cells of 1.5 volts each in series with the ammeter, leaving a gap XY in the circuit as shown here. Complete the circuit by connecting the nichrome wire in the gap XY. Plug the key. Note down the ammeter reading. Take out the key from the plug. Replace the nichrome wire with the torch bulb in the circuit and find the current through it by measuring the reading of the ammeter. Now repeat the above step with 10-watt bulb in the gap XY. Are the ammeter readings different for different components connected in the gap XY? What do the above observations indicate? Yes. Thus, the motion of electrons through a conductor is retarded by its resistance. A component of a given size that offers a low resistance is called a good conductor. A conductor having some appreciable resistance is called a resistor. A component of identical size that offers a higher resistance is called a poor conductor. An insulator of same size offers even higher resistance. Factors on which the resistance of a conductor depends. Let us do an activity. Set up the circuit by connecting 4 dry cells of 1.5 volt each in series with the emitter, leaving a gap XY in the circuit as shown here. Replace the nichrome wire by another nichrome wire of same thickness but twice the length, that is 2L. Note the emitter reading. Now replace the wire by a thicker nichrome wire of the same length L. A thicker wire has a larger cross-sectional area. Again note down the current through the circuit. Instead of taking a nichrome wire, connect a copper wire in the circuit. Let the wire be of the same length and same area of cross-section as that of the first nichrome wire. Note the value of the current. It is observed that the emitter reading decreases to 1/2 when the length of the wire is doubled. The emitter reading is increased when a thicker wire of same material and of same length is used in the circuit. A change in emitter reading is observed when a wire of different material of the same length and same area of cross-section is used. On applying Ohm's law, we observe that the resistance of the conductor depends on its length, on its area of cross-section, and on the nature of its material. Precise measurements have shown that the resistance of a uniform metallic conductor is directly proportional to its length, L, and inversely proportional to the area of cross-section, A. That is, R is directly proportional to L and R is inversely proportional to 1/A, where RHO is a constant of proportionality and is called the electrical resistivity of the material of the conductor. The SI unit of resistivity is ohm meter. It is the characteristic property of the material. The metals and alloys have very low resistivity in the range of 10 raised to the power -8 ohm meter to 10 raised to the power -6 ohm meter. They are good conductors of electricity. Insulators like rubber and glass have resistivity of the order of 10 raised to the power 12 to 10 raised to the power 17 ohm meter. Both the resistance and resistivity of a material vary with the temperature. Resistance of a system of resistors. Combination in series. There are 2 methods of joining the resistors together, such as series and parallel. Make an electric circuit and the resistors having resistances R1, R2 and R3 respectively are joined end to end. Here the resistors are said to be connected in series. Here the resistors are said to be connected in parallel. Join 3 resistors of different values in series. Connect them with the plug key, battery and an emitter as shown here. Plug the key. Note the emitter reading. Change the position of the emitter to anywhere between the resistors. Note the emitter reading each time. Do you find any change in the value of current through the emitter? You will observe that the value of the current in the emitter is the same independent of its position in the electric circuit. It means that in a series combination of resistors, the current is the same in every part of the circuit or the same current through each resistor. Set up the electric circuit and insert a voltmeter across the ends X and Y of the series combination of 3 resistors as shown here. Plug the key in the circuit and note the voltmeter reading. It gives the potential difference across the series combination of resistors. Let it be V. Now measure the potential difference across the 2 terminals of the battery. Compare the 2 values. Take out the plug key and disconnect the voltmeter. Now insert the voltmeter across the ends X and P of the first resistor. Plug the key and measure the potential difference across the first resistor. Let it be V1. Similarly, measure the potential difference across the other two resistors separately. Let these values be V2 and V3 respectively. Deduce a relationship between V, V1, V2 and V3. You will observe that the potential difference V is equal to the sum of the potential differences V1, V2 and V3. The total potential difference across a combination of resistors in series is equal to the sum of potential difference across the individual resistors. That is, V is equal to V1 plus V2 plus V3. Let I be the current through the circuit. The current through each resistor is also I. It is possible to replace the three resistors joined in series by an equivalent single resistor of resistance R, such that the potential difference V across it and the current I through the circuit remains the same. Applying the Ohm's law to the entire circuit, we have V is equal to IR. On applying Ohm's law to the three resistors separately, we get to know that V is equal to V1 plus V2 plus V3. IR is equal to IR1 plus IR2 plus IR3, or RS is equal to R1 plus R2 plus R3. So we can conclude that when several resistors are joined in series, the resistance of the combination RS equals the sum of the individual resistances R1, R2, R3, and thus is greater than any individual resistance. Heating effect of electric current. If the electric circuit is purely resistive, that is, a configuration of resistors is only connected to a battery, the source energy continually gets dissipated entirely in the form of heat. This is known as the heating effect of electric current. This effect is utilized in devices such as electric heater and electric iron. Let us do an experiment to understand the heating effect of electric current. Take a beaker and fill it with water. Now take a nichrome coil. It is the glowing coil in a heater. Immerse the nichrome coil in the water and connect it with an electric circuit as shown. Remember, that should be a battery with 6 cells. Note down the reading of thermometer. Now switch on the key and wait for 5 minutes. Now switch off the key and again take the reading of thermometer. What do you observe? The temperature of thermometer has increased. As the current was flowing through the nichrome wire for a long period, it heated the wire. The water in which nichrome was immersed absorbed the heat of nichrome and hence its temperature increased. So we have seen that when an electric current flows through a circuit for a long time, a heat is produced in the circuit. This is termed as the heating effect of electric current. Consider a current I flowing through a resistor of resistance R. Let the potential difference across it be V. Let T be the time during which a charge Q flows across. The work done in moving the charge Q through a potential difference V is VQ. Therefore, the source must apply an energy equal to VQ in time T. Hence, the power input to the circuit by the source is P is equal to VQ by T is equal to VI. The energy supplied to the circuit by the source in time T is PT, that is VIT. What does happen to this energy expended by the source? This energy gets dissipated in the resistor as heat. Thus, for a steady current I, the amount of heat H produced in time T is H is equal to VIT. Applying Ohm's law, we get H is equal to I square into RT. This is known as Joule's law of heating. The law implies that heat produced in a resistor is directly proportional to the square of current for a given resistance, directly proportional to the resistance for a given current, and directly proportional to the time for which the current flows through the resistor. In practical situations, an electric appliance is connected to an unknown voltage source. Practical applications of heating effect of electric current are electric heaters, bulbs filaments, electric fuse, electric kettle, sandwich maker, toaster and electric iron. Electrical power. Look at these electrical appliances. Which one of these consume more electricity? Of course, 250 volt bulb. Thus the power is defined as the rate at which electric energy is dissipated or consumed in an electric circuit. This is also termed as electric power. The power P is given by P is equal to VI, or P is equal to I square R is equal to V square by R. The SI unit of electric power is watt or W. It is the power consumed by a device that carries 1 ampere of current when operated at a potential difference of 1 volt. Thus, 1 watt is equal to 1 volt 1 ampere is equal to 1 VA. The commercial unit of electric energy is kilowatt hour or kWh, commonly known as unit. 1 kilowatt hour is equal to 1000 watt into 3600 seconds is equal to 3.6 into 106 watt seconds is equal to 3.6 into 10 raised to the power 6 joule. Combination in parallel. Make a parallel combination XY of 3 resistors having resistances R1, R2 and R3 respectively. Connect it with the plug key or battery and an ammeter as shown here. Also connect a voltmeter in parallel with the combination of resistors. Plug the key and note the ammeter reading. Let it be I. Also take the voltmeter reading. It gives the potential difference V across the combination. The potential difference across each resistor is also V. This can be checked by connecting the voltmeter across each individual resistor. Take out the plug from the key. Remove the ammeter and voltmeter from the circuit. Insert the ammeter in a series with the resistor R1 as shown here. Note the ammeter reading I1. Similarly, measure the currents through R2 and R3. Let these be I2 and I3 respectively. What is the relationship between I1, I2 and I3? It is observed that the total current I is equal to the sum of separate currents through each branch of the combination. I is equal to I1 plus I2 plus I3. Let Rp be the equivalent resistance of the parallel combination of resistors. By applying Ohm's law to the parallel combination of resistors, we have I is equal to V divided by Rp. Let it be equation 1. On applying Ohm's law to each resistor, we have I1 is equal to V divided by R1, I2 is equal to V divided by R2 and I3 is equal to V divided by R3. Let it be equation 2. From equations 1 and 2, we have V divided by Rp is equal to V divided by R1 plus V divided by R2 plus V divided by R3, or 1 divided by Rp is equal to 1 divided by R1 plus 1 divided by R2 plus 1 divided by R3. Thus we may conclude that the reciprocal of the equivalent resistance of a group of resistances joined in parallel is equal to the sum of reciprocals of the individual resistances.